Hello everyone, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. Today in this video, I am going to talk about particle in a box. So, how you will approach particle in a box? So, step 1, define the potential energy. First, define the potential energy. Then solve the Schrodinger equation. If you know the potential energy, then solve the Schrodinger equation. Then define the wave functions. Then determine the allowed energies and then interprets its meaning. So total 5 steps you can do step by step. So first, particle in a one-dimensional box, infinite walls. So define the potential. This is the reason where potential is infinitive. This is the reason where potential is infinitive. This is the reason where potential is 0. This is the total length 0 to L in x direction. So time independent Schrodinger equations, we have kinetic energy, these portions. This portion is potential energy. This is the total energy. So applying boundary conditions here, listen 1 and 1, 3. Then you will get this minus h cross square by 2m d square psi x by dx square. Here potential energy for 1 and third is infinitive. So this psi and a psi. And you know the probability density is equal to 0. So this is the second derivative of the function equal a negative constant time the same functions. So this is the functions with these properties, sine function and cos functions. So for reason 2, you will get like this values. This is similar to the general differential equations like psi is equal to a sine kx plus b cos kx. Then apply boundary conditions. Boundary condition, if it is 0, then b is equal to 0. If L and 0, then you will get the n pi x L a sine. But what is a here? So normalized wave functions you make. This is the normalizations conditions. You will get the root 2 by L. Thus normalization wave function is this equation. Now, calculate the energy. After calculation of this energy, with each step you will get E is equal to n square is squared 8m L square. Now, particle in a one-dimensional box, energy level E1, E2, E3. Then you have the psi 1, psi 2, psi 3. This is the psi 1, this is the psi 2, this is the psi 3. And this is your distance. And then a square. So difference between adjacent energy level, del E is equal to En plus 1 minus En, total 2n plus 1 E1. Second, non-zero, 0 point energy. And probability density, this one, is a structure with reason of the space demonstrating enhancing the probability. A very high value n value spectrum become continuous and convergence with Cm, which is the Bohr's corresponding principle. So here you can see the differences E1, E2, and then from E2 to E9 you see the big difference, here less difference. Here in psi 1, psi 2 also. Here positive, negative both, but in case of modes square, probability of electron is only positive. Now, particle in a three-dimensional box, you can apply in x, y, z all, and then you will get this equations. ns square by a square, n square by b square, n square, z by c square, like this. So, the question is, an electron is in one-dimensional box of 1 nanometer length. What is the probability of locating the electrons between x is equal to 0 and x is equal to 0.2 nanometer and its lowest energy state? So, how you calculate such type of problem? You can see. Question, an electron is one-dimensional nanometer. So, you have the P x1 to x2. This is the formula. Now from initial x1 to x2, do the mathematics, you will get this 0.05 nanometer. So what are the most likely location of particle in a box of length L in the state n is equal to 3? So n is fixed. So you can use this. What are the most likely location of particle in a box of length L in state 3? You can see, you know the psi 3 formula. Then you can use these conditions and you will get these values. Now expectation value of position and its uncertainty. Expectation value, it is defined by this x. Then you will get the expectation value L by 2 and uncertainty L square n square pi square minus 6 12 n square pi square. You do the mathematics all. Then expectation value of momentum and square of momentum. So expectation value of momentum and square of momentum, you will get these values. Now estimating pigment length. You have this. This is the length, total 1, 2, 3, 5, and here is the small length, angstrom. So each atom in the path of the contribution 1 electron to the quantum energy level inside the box. For considering, by Pauline's principle, only 2 electrons can occupy the same energy state. So have the same energy, but they must have opposite spin. Now a typical bond length in the path of the conjugation is 1.4 angstrom. So you can see ground state of the molecules and excited state of the molecule. N is equal to 1, N is equal to 2, N is equal to P by 2, N is equal to P by 2 plus 1. So here up and down. Now here without orientations. So first excited state of the molecule. Now electrons J square by I square H square ml square, put the all value P by 2 plus half. You will get this. So E photon is equal to E electrons. So apply SC by lambda and then this equation. Cancel out H on both sides. You will get these relations. Now wavelength of transition of 4 anthracene. Particle in a box, this one, and this is the length. And this length is 6 angstrom. So in pi electron considered free in the box of the length L. Ignore all Coulombic interaction. So pigment and quantum mechanics. This is the beta carotene, lycopene, echinone. High degree of conjugation. Electrons have the wave properties and they don't jump off the pigment when they reach its ends. So these electrons' resonance determine which frequency of light, thus which color are absorbed and emit from the pigment. So yeah, we will calculate easily with the help of quantum chemistry. So electron resonance in a cyclic conjugated molecules. You can see this is your cyclic conjugation. A crude quantum model for such molecules assumes the electrons moving free in a ring system. So resonance condition 2 pi r in lambda, and r is the radius of molecules and lambda is the wavelength of electrons. So you can easily calculate E electrons NH 2 pi r and E electron half mv square and n square h square 8 pi square r square. The energy is once again quantized and depends on variable in which possesses discrete values only. So this is very important formula and a very good applications like anthracene. You have different pigment, you have the chlorophyll A and chlorophyll B and porphyrin ring. You also know the ground state and excited state. How ground state and excited state you will calculate with the help of quantum mechanics. So my friends, I hope this video will be helpful to you. If you like this type of video, then subscribe my channel, and thanks for watching.